it's a great pleasure to have Sebastian visiting us from Columbia University. Columbia is now deemed to be a local institution because it's within easy car travel of this is sort of part of our plan to allow for backups in case of problems. And this is the first live JQI seminar since March of 2020. And the first time we've tried in this hybrid mode. So it's a real honor to have Sebastian here to put it through the runs. He's actually a person of some long experience in ultra-cold atom physics. He did this as an undergraduate. He worked in Wolfgang Ketterle's laboratory. He got a diploma in 2005, and 2006 got his diploma Arbeit. Shortly after that, he worked with Emanuel Bloch both in Mainz and at the Max Planck Institute in Germany. So he's familiar with building up and tearing and transporting apparatus all over the place. And he was with Vlad and Vuletic in MIT, and now he's since 2016, I believe, has been an assistant professor of physics at Columbia University. And well, he's working on ultra-cold atoms, which he's going to tell us about today.
All right, thanks so much, Charles, for the introduction, and well, thanks so much for the invite. I mean, it's a great honor to be here. It's for me also the first talk, in-person talk. Maybe I take off the mask. The first in-person talk in 18 months, and it feels very special, I have to say. And I'm very excited to tell you a bit about our progress at Columbia University on creating ultra-cold dipolar NaCs molecules. Okay, you get used to this guy. Aha. So yeah, it's working. Thanks, Alicia. So basically, the gist of the talk is already on the first 3 slides. So we are creating Bose-Einstein condensates of sodium and cesium, and basically we want to get ground state molecules of sodium cesium out of these ultra cold quantum gas mixtures of sodium and cesium. Well, the past 18 months basically felt like sitting in a cocoon myself and also the research group. Not much interactions outside, not many talks and conferences, only online, of course. You know, when we had these conferences, maybe we felt like that, but most of the time felt like that. So it's really great to be out again. And I really wanna give credit right at the start of my talk to my group, who has just done amazing during the COVID time. Really stayed encouraged and really energized and motivated. And all the results, basically all the results I tell you today about is results from the last year, or 1.5 years. So let's get to it. When you read the abstract, you may have seen the first sentence that I wrote, that ultra-cold molecules combine features of ultra-cold atoms and trapped ions. Well, that's maybe not the most precise sentence that I ever wrote in my life, but I still want to tell you what I mean by that. So for ultra-cold atoms are neutral atoms. System sizes are, you know, from 1 to 100,000, maybe a million atoms. We have contact interactions that are controllable. And we can optically trap the atoms, and we can make artificial crystals by trapping them in optical lattices. For trapped ions, the ions are charged, system sizes maybe up to 1,000 ions or so. Then we have long-range Coulomb interactions, and we can have crystals of these ions in the traps, 1D and 2D. Okay, so what about dipolar molecules? Well, dipolar molecules are also neutral like atoms. System size as well is hard to say because it's still a new field, but let's say currently around 10,000. There we have now long-range interactions, controllable long-range interactions between the molecules. We can optically trap them like neutral atoms. And perhaps there's a chance to still see crystallization making use of these dipolar long-range interactions. So basically, I found in a textbook, I forgot the exact reference, but this nice sentence: a dipole is the second most important charge distribution after the point charge. So yeah, if you got to be neutral, well, at least you can have a dipole. So that's what motivates us. So let's quickly remind ourselves what is dipolar interactions like. When two dipoles meet side by side, they have interaction, a long-range interaction that goes as 1 over r cubed, described like here. And it is long-range, anisotropic. So when dipoles meet head to tail, they attract each other. When they meet side by side, they repel each other. And in this sense, they can be attractive and repulsive. So just to contrast this with the contact interactions that we have usually with ultracold atoms, in ultracold atoms, contact interactions are expressed by a delta function, which basically means ultracold atoms interact when the wave functions overlap. So basically, the atoms need to touch each other. While long-range interactions, they act at a distance, and yeah, we have this 1 over r cubed behavior for molecules. So why are the molecules interesting? Well, one is the dipolar interactions. The other part is the interesting internal structure that's much more involved than atoms. In molecules, you have like between the two atoms in a diatomic molecule, like a molecular potential, like sketched here, like a Born-Oppenheimer type potential. And in this potential, there live vibrational states that are typically spaced, by terahertz energy scales. Then you have on top of these vibrational states living rotational states, typically spaced by tens of gigahertz or 10 gigahertz. And then on top of that, you have a hyperfine structure that in the case of bialkali molecules that we are dealing with, can have splittings at typical magnetic fields as small as 100 kilohertz or so. So just looking at this 100 kilohertz energy scale, you basically see that if you want to have quantum state control in these molecules, you need to have temperatures smaller than 1 microkelvin, not micrometer, sorry for the typo. And the molecules are particularly interesting when being in this absolute ground state. That's where the dipole moment is strongest. So we are especially interested in putting molecules into this absolute ground state here, the lowest row vibrational state. So with these molecules, there have been, over the last 2 decades, actually amazing proposals of what one could do. In the lab, it turned out quite challenging to actually get to this point of implementing these proposals. But basically, there are predictions of novel many-body quantum phases. There is the proposal, and there have been early experiments on quantum simulation of quantum magnetism with molecules in optical lattices. Using the long-range interactions between molecules for quantum information is a very early proposal by Dave DeMille, but it also turns out that molecules can have hyperfine states, which have very long coherence times. So you can think of quantum memory and quantum processing in the same physical system. And then there's also the quantum chemistry part, understanding collisions of ultracold molecules and really trying to understand them from first principle. That's really a new frontier that opened up. But of course, these are the proposals. But once we have the experiment, probably the most exciting thing is to actually figure out what can be done, what nobody has thought of before. So it's an exciting new system. So just to give you sort of a visual impression, what kind of systems we are thinking of. So ultracold molecules, you probably have heard, you can actually laser cool molecules. Some specific molecules have been successfully laser cooled. I think temperature records are on the order of microkelvin and phase-space density of 10 to the minus 6 or so. So that is still quite a bit away from quantum degeneracy. In our case, we're actually focusing on molecules that are close to, we want to get them close to quantum degeneracy to observe interesting new phases. So the picture that kind of applies to our case is we have molecules trapped in, let's say, a harmonic trap, and they are a few hundreds of nanokelvin cold, and the sample has the extent of a few tens of micrometers. The molecules itself, are diatomic bialkali molecules where the atoms are spaced by, a few angstrom. And the dipole moments of bialkali molecules range between 0.5 and 5 dBi roughly. So here from earlier work at MIT, where we actually created the first NaK ground state molecules, there's a picture of a cloud of a few thousand of such ground state molecules. Okay, so with these bialkali molecules, also a notorious thing that turned out to be quite challenging in the early years, and still has a lot of open questions, is the question of chemical reactions in binary collisions of molecules. So when you have two of these molecules, you can have a chemical reaction that species AB makes up the initial molecules and can make in a collision A2 plus B2. So some of the bialkali molecules have this chemical reaction allowed, energetically allowed. But they are also chemically stable molecules. We kind of prefer them because this kind of intrinsic loss channel is not there. NaCs is one of the chemically stable molecules, and NaK as well. But there are other loss mechanisms, so it has been hard to tame molecules in the experiments that have been going on so far. Okay, so this was sort of the general introduction. Let's get to what I want to talk about today. So first, I want to give you a brief overview how we make these dipolar molecules, why we are interested in sodium cesium, then going to the results that we got. We have created overlapping condensates of sodium and cesium. We have created near-degenerate sodium cesium Feshbach molecules, and we have made progress towards the NaCs ground state. And in the end, if there's time, but I fear there may not because we start a bit late, I tell you about another experiment where we try to induce long-range interactions in atomic arrays, unrelated to molecules. So let's get going with number one. So how do we make dipolar molecules? Well, in some sense, we assemble them atom by atom. Well, not by grabbing single atoms, but by overlapping mixtures of two different atomic species and binding them together. So there we are basically following pioneering work of making this possible by Debye, by Junier, and by Hans-Christoph Nägel, who showed these things for the first time. So what do we do? Well, first of all, we make use of Feshbach resonances. Feshbach resonances between ultra-cold atoms, as a tool to tune scattering lengths between colliding atoms if you tune a magnetic field. But this tuning of scattering lengths actually becomes possible because a molecular bound state between two free atoms comes into resonance as a function of magnetic field with two colliding free atoms. So this bound state is the reason why you can tune the scattering lengths. And in turn, you can use this as a way to actually bind two free atoms into a molecule by sweeping the magnetic field adiabatically from above the Feshbach resonance to below the Feshbach resonance. So that's what we use to actually make in the first step our molecules. We dial the magnetic field, control the interactions between in our bialkali mixture, and make weakly bound Feshbach molecules. So for this, we need to find Feshbach resonance first, of course. Then going from the weakly bound Feshbach molecules, which are actually very fluffy molecules, very extended, there's a huge distance between the atoms. We actually want to go to the absolute ground state, which means we want to shrink them. We want to take out the binding energy. This corresponds to about 7,000 Kelvin worth of vibrational energy. And we want to do that in a way that we don't heat the whole ensemble, forming then a tightly bound ground state molecule. And the way to do that is via a two-photon process that is making use of the stir-up concept, stimulated Raman adiabatic passage. I will give you more details on that later. So that's sort of the basic overview, what you do. So why NaCs? For that, the key motivation is the dipole moment itself. So if you look at possible bialkali molecules, the ones listed are actually bialkali molecules that have been created before, at least here below the first row. There you see that the dipole moment is somewhere between 0.6 dBi and 3.3 dBi. So sodium cesium has even larger dipole moment than the other dipolar molecules that have been created in the lab. And due to a favorable ratio of the dipole moment and the rotational constant in sodium cesium, also only a fairly small electric field is necessary to align the dipole moment in the lab frame. So it turns out when you have no electric field present, you actually have no dipole-dipole interactions. Only when you align the dipole in the lab frame, you actually induce a dipole moment and you switch on the interactions. And for sodium cesium, already at fairly moderate electric fields, you get really large induced dipoles. So this is very powerful, hopefully for studying new physics. So that is one motivation. Oops. Yeah. Then let's look into some of the phases that we are interested in our system. So in here particular, we are interested in 2D systems of dipolar molecules. And the physics of dipolar molecules in 2D system can be basically understood by a Hamiltonian that expresses the kinetic energy of the molecules and the interaction energy between the molecules. So you get a competition between kinetic energy and interaction energy. So, visualizing molecules in a 2D system like that, we imagine the dipoles being perpendicularly aligned with respect to the 2D plane, and they repel each other. Now, I told you before, via side-by-side collisions, I told you before that in some molecules, you have issues with losses, like chemical reactions or other loss processes. So here in this 2D geometry, it's advantageous because with repulsive side-by-side collisions, you're actually avoiding two-body collisions between the molecules. So you're stabilizing the system. This was discussed in early works and also by Paul Julian, characterized for different bialkyl molecules that this can be effectively stabilizing the mixture or stabilizing the molecular system. So quantum chemistry can be prevented, and any losses that are induced by the trapping light can be also prevented. Two-body losses induced by trapping light. So this Hamiltonian, as innocent as it looks, actually has some interesting phases that are expected. So here you see a schematic phase diagram. Well, it's actually not only schematic, it's sort of quantitative also. Here on the y-axis, you have temperature. On the x-axis, you have effective strengths of dipole-dipole interactions. So this RD is the ratio of the characteristic length scale of dipolar interactions divided by the interparticle spacing. And basically, you see here when you are, more or less weakly interacting dipolar-wise, you get a dipolar superfluid. That's a prediction. When you are increasing the external field, you would align the dipole moment more strongly in the lab phase. You should actually be able to get a crystalline phase. That would be very exciting to observe, a crystal of dipolar molecules. So you have an interesting phase transition between a superfluid and a crystal into D. So that's actually a long-standing questions that are associated with that. And then you have also interesting finite temperature transitions. For example, the question of what happens when you actually melt a 2D crystal of dipolar molecules. So this is an interesting Kosterlitz-Dawlis transition, which has a couple of open questions associated to it. Would be great to study that. So there are some, more exotic predictions. It's like, is there perhaps a super solid phase between the superfluid and the crystal, and there may be a hexatic phase when melting the crystal when raising the temperature. So these are things that we would really like to study.
What characterizes a hexatic phase?
So you have actually the translational symmetry is restored, but you still have a rotational symmetry. So you have hexagonal symmetry, but translationally it's invariant. So there is a question associated with that, whether you have actually two transitions when you are raising the temperature of the crystal. So now, kind of looking at that phase diagram, we want to understand what kind of molecular properties do we need to actually study it, and that, assuming some sort of experimentally realistic parameters, it turns out that all the dipolar molecules that have been made so far are actually expected to be somewhere in the superfluid regime in this phase diagram. If we start plotting sodium cesium here, it actually turns out that sodium cesium should allow for realistic experimental parameters to study the full phase diagram. So sort of maximum interaction that can be achieved is RD50. So yeah, to actually get two sodium cesium ground state molecules, we need to go through the full exercise, first creating a sodium cesium mixture, create Feshbach molecules, go to the absolute ground state with a 2-photon process that carries our Feshbach molecule via stirrup into the absolute ground state. So that's the plan. And sodium cesium has never been studied before. So basically as a mixture. So basically we are in new territory here as an ultracold mixture. So the challenges are, so that sodium cesium mixtures have never been studied. It's actually the last bialkali mixture that has to be explored at ultracold temperature, and the scattering properties are predicted, but not experimentally known. And then on top of that comes that cesium is notoriously difficult atom to deal with because the background scattering length is somewhere at 2000 A0, and you have a bounding 3-body loss that you need to deal with. On top of that comes that you cannot trap it magnetically. So it sounds like very difficult, the whole thing, which is probably the reason why nobody really looked at it seriously before. So we have made progress on that. We started in an empty lab with our stuff in July 2018. So Charles said that I started at Columbia in 2016. That's true. I truly started, though, being present at 2017. But Columbia University took almost 2 years to get the labs ready for me. So that was an ordeal. But as soon as we had the labs ready, we really tried to push it. So empty labs in July 2018. Then first we started working on sodium, made a sodium BEC. Then we worked on cesium, making a 2D mod, a 3D mod. And then came the COVID shutdown. So for 3 months, nothing happened. After the COVID shutdown, we resumed and very quickly got dual BECs of sodium and cesium about a year ago. And then we pushed forward towards ground state molecules. And I will tell you about each of these steps a bit more. So yeah, empty lab here. But that's how it looks today. The laser table for laser cooling sodium and cesium. And that is the experiment table. So here you see this kind of tower in the back. That's actually the vacuum chamber where the experiments happen. And all the optics around to guide laser beams into the chamber. It's a very high, ultra high vacuum chamber. I think we have pressure of 10 to the minus 12 torr, probably the emptiest place in New York City. Then we zoom here into this vacuum chamber. Then we create a Mott here of sodium atoms, about 5 to 10 billion sodium atoms in there. So that's sort of the sodium part. And then gets us to the next item of making condensates of sodium and cesium. So we are at the first step of our way towards ground state molecules of sodium and cesium. And our work there has been recently published, actually just a week ago, on the first sodium cesium condensates. So for sodium, we do a kind of a standard procedure. We trap sodium in a magnetic trap and use an optical plug and evaporate sodium in this optically plugged magnetic trap, and we get nice condensates there. So nothing special for sodium. For cesium, actually, we did the one thing that starts to be unusual on the technical side. We use a 2D mod. We designed a 2D mod for cesium, a very compact source that actually works very well and allows us to load very effectively, roughly 1 billion cesium atoms within 1 second into a 3D mod. So that's actually turned out very nice and much preferred over Zeeman-Slower. That is much more common for cesium cooling. So with that, we loaded a 3D mod of cesium, and we went through the standard scheme of cooling cesium, which was actually developed by Steve Chu and collaborators Vladan Vuletic and Cheng Chin were part of it too, of how to cool cesium to ultra-cold temperatures. Well, first you make a Mott, then you do optical molasses, and then you do what's called degenerate Raman sideband cooling to actually get the temperature down so low that you can do optical trapping. That was believed to be the standard sequence. And that is what we did just before the COVID shutdown. So we have here our 2 microkelvin cold cesium cloud. All that works great, but it turns out it's not necessary. So a long-held wisdom about cesium cooling, it gets questioned here, and I have to give credit to my postdoc, Ian Stevenson, who really figured that out, that this is possible, and it's actually one of the reasons why we have been able to move extremely fast on this. So we do sympathetic cooling of cesium with sodium, and we load against common wisdom cesium into the magnetic trap together with sodium into the optically plugged trap, and do evaporative cooling in the magnetic trap. And here you see the phase space density increase of cesium as a function of atom number. And you see for cesium that the phase space density goes straight up during sympathetic cooling. That is what we love to see in the lab. You basically cool without you losing atoms. So that is just amazing. So the cooling in the magnetic trap of cesium works amazingly well. It's all about the timing, though. You don't want to go too long, and so the cesium cloud doesn't become too dense. So 3-body losses kick in. So we kind of need to hand it over. And then we hand it over into an optical dipole trap that's actually made up of 3 beams. It's a crossed dipole trap with crossing under 90 degrees. And then there's another optical beam with a high volume, a high power trap up to 100 watts to increase the volume of that trap. So it's sort of a dimple trap. And if Ian Spielman is on the call, basically we also switch on these dipole traps during the magnetic trapping. So it's also a hybrid trap in some sense. And in this trap, we actually cool down the mixture and get dual condensation. So here you see dual condensates with phase space density above 1. Here you see pictures. So basically here, the first picture is at the beginning of optical trap loading, and then we keep on evaporating optically until we have about 1 million of sodium atoms and 40,000 cesium atoms in the condensate. So these numbers are very good compared to many other experiments. So this is worked much better than we could have even dreamt of. And there's another thing that's special, and also part of the reason why it works so well. So in the optical trap, sodium and cesium are overlapping extremely well. It turns out, and that's something I thought of before, but again didn't imagine how useful it is. At 1064 nanometer trap, the differential gravitational sag between sodium and cesium is very small because the trap frequencies turn out to be almost equal. So the clouds overlap with each other despite the huge mass difference, and that allowed us actually to study very nicely cross-thermalization between the clouds, which allowed us to measure the intraspecies scattering lengths, and that told us that it's weakly repulsive, which is the reason why these mixtures are truly miscible. So none of this was known experimentally, so we kind of need to figure it out. So for miscibility, you want to have like a ratio of these interaction parameters G to be larger than 1. And turns out for our sodium cesium mixture, at the 2 working points that we like to work at, 23 Gauss and 894 Gauss, we are in the miscible regime, and the clouds really overlap, and even more so, the BECs overlap. And that's actually something, again, quite unique. There is not a lot of bialkali mixtures. Actually, I think there's only sodium rubidium that can be tuned into a regime where you have 2 BECs actually overlapping. So it's 2 overlapping superfluids. And it's not something we had thought of much before, but that may actually open up some real interesting new physics about studying overlapping and interacting superfluids. And of course, another possibility is polar physics of this mixture. But it's not something we have looked into deeply. But if on the theory end someone has ideas, this would be very, very nice to hear about, because yeah, it's actually quite unique. Then we look at the lifetime of our mixture of sodium and cesium condensates. And first, we look at our condensates alone. We see that for sodium, the condensate persists for more than 200 seconds in our optical trap. That's very long. Cesium, when it's produced alone, it actually becomes thermal just after 2 seconds. That's when the BCs are just by themselves, not a mixture. Turns out when you put them together, sodium and cesium, sodium stays condensed for more than 300 seconds, and cesium stays condensed for all the time that we looked, here in this case 30 seconds. So it turned out also this nice overlap between the mixture keeps cesium condensed, because there is continued sympathetic cooling between the mixtures, or cesium is sympathetically cooled by sodium, even when it's held as a BC. So what we care most about is that these are ideal conditions for the creation of ultracold sodium cesium molecules. You have overlapping condensates, something unique in bialkali mixtures. Okay, so let's go to the next step, making Feshbach molecules. Well, turns out there have been some predictions about Feshbach resonances in sodium cesium. And the best prediction was by Debye 15 years ago, that there should be, in the absolute hyperfine state of the mixture, or in the absolute hyperfine state of sodium cesium, in that channel, there should be a resonance at 840 Gauss, 1 Gauss wide. So that doesn't sound great. You need to generate high magnetic fields, and you need to be rather stable. But we used that guidance to actually locate the Feshbach resonance, and we found Feshbach resonance at 864 Gauss. So pretty close to the prediction that we just measured via trap loss. But something that I didn't mention so clearly before, initially we need to prepare the sodium cesium mixture at a magnetic field of 894 Gauss, because that's where the scattering length intraspecies of cesium is kind of manageable, weakly repulsive. But the Feshbach interspecies Feshbach resonance is at 864. So we need to change the magnetic field. And while changing that magnetic field, the cesium scattering length changes dramatically. So for sodium, the scattering length as a field, functional field, is almost constant, so very uncritical. For cesium, it's kind of scary. One doesn't know what happens once you start changing the magnetic field from about 900 Gauss to where the Feshbach resonance is. So, well, we tried to go quick. So we built like a circuitry that allowed us to actually, change this field just within 2 milliseconds and go across the Feshbach resonance. And actually, that allowed us then to make quite efficiently Feshbach molecules, or reasonably efficiently. Then we clean out remaining atoms that have not been associated using a magnetic field gradient, and then can work with these Feshbach molecules. So for example, we can image the Feshbach molecules after dissociation, and we detect about 40,000 molecules. That's a lot of molecules. There's, again, not many ultra-cold molecule experiments that have these kind of numbers. It's like the KRB at Gila, as of recently, has maybe 100,000 or even a bit more, but this is very good as the first go. At MIT with NAK, we had like 4,000 molecules. That's a question.
What's the time scale for actually forming the Feshbach?
Yeah, so the question is about the time scale of the formation process of the Feshbach molecule. Yeah, basically it has to do with how strong is the coupling between the molecular bound state and the free atom state, and there, with respect to that sort of energy gap between this of this avoided crossing that emerges, you need to be slow compared to that. So in our case, we can actually go at a fairly fast speed because the coupling is sufficiently large. I cannot give you a precise number. I can't give you the ramp rate, but
Substantially faster than 2 milliseconds.
Yeah, substantially faster than 2 milliseconds. Yeah, it's like here we do 30 Gauss in 2 milliseconds, so it's like 10 Gauss in a millisecond is the ramp rate or something. And we have played with that, and basically we are in the in the saturated regime. So yeah, so here we have these 40,000 molecules. Actually, it's a fairly high density, 4 × 10⁻². It's very, very nice. Interparticle spacing is less than a micron. That's a good number to keep in mind for later. And then we did a precision measurement of the Feshbach resonance location also. We measured the binding energies of the Feshbach molecules. I go here a bit faster because that's super essential, but it allows us to parameterize the Feshbach resonance very precisely. And we did that in collaboration with Debye Thiemann, who did the Kappa channels calculation. And we need these parameters for something else in a second. Yeah, we see that just below the Feshbach resonance, we are already closed channel dominated. So that's helpful for the stirrup process as well. So now next thing we want to do is actually we want to measure the temperature. Well, one should be careful and not call it temperature probably, but mean kinetic energy, because our Feshbach molecules don't thermalize, at least not in an obvious way. But it turns out we need to, in our measurement sequence, we need to measure in a way that we dissociate the molecules and then look at the time of flight expansion of the cesium atoms after dissociation. Now, the thing is, when you do that, when you dissociate, you actually add some kinetic energy to the atoms, because when you dissociate, you kind of, when you are not adiabatically dissociating, you get a little bit of energy offset that is a function of the ramp speed of the return ramp of the dissociation ramp. So here you see a time of flight expansion of our cesium cloud after, cesium atoms after dissociation, and we can extract from that a temperature from this time of flight expansion. But keep in mind, so these, this time of flight expansion is having an energy in it that comes from the finite ramp speed of dissociation. So we need to do this measurement for many different ramp speeds. And then we can extrapolate to the temperature of the molecules before they were dissociated. There is some theory for that, how to actually fit this line. Once we do that and extrapolate to 0 ramp speed, to a really adiabatic dissociation ramp, we can actually get a number for the temperature. And if we start plotting that, it looks quite interesting. So let's look here at just at the bottom plot. You see here that there is a data point where we actually see temperatures that are in the range of 10 nanokelvins. We get that when we associate Feshbach molecules from 2 overlapping BECs. So we can do, since we have this control over our mixture, we can do association from 2 thermal clouds, from sodium BEC plus a cesium thermal cloud and 2 BECs. So as expected, when you associate from 2 BECs, you get extremely cold molecules. And it seems like we get like a 10 nanokelvin range cold clouds. But with this dynamic range, basically we can decide whether we want to make 20,000 molecules at 900 nanokelvin or 600 molecules at like, here 18 nanokelvin. So this is very nice dynamic range to have, and it may be for us a pathway to make really cold ground state molecules. An open question in ground state molecules, especially in bosonic ground state molecules, is making a BEC of ground state molecules. That has never been done before. Maybe we have here a pathway to that.
What's the kind of the main setback to that? Like, why not?
The main setback is that it's hard to associate Feshbach molecules at cold temperature to start with, because you kind of need overlapping BECs for that. So that is something we have no access to.
Getting the material.
Right. So there's 2 ways. You can start cold and transfer the cold Feshbach molecules into the ground state and stay cold. The other thing is you can first start hotter, thermal, go to the ground state and try to do evaporative cooling. But that is still in a very early stage. There have been some early works in the recent 2 years about evaporation, but of potassium rubidium and of lithium sodium, but it's still hard to do that. So if you can start cold to begin with, this should be an easier route. And it turns out on the experimental side, this is all stuff from the last year. There is room for improvement on several levels, and some of the improvements we have done already, and see substantial boost of performance, which I haven't prepared for the talk, but it looks quite good. And just to convert the numbers that I showed before in terms of phase space density, so it seems like we can have here a point of bosonic Feshbach molecules that has a phase space density within the degenerate regime. Again, it's a bit tricky because the molecules don't thermalize or don't thermalize effectively, but it's very promising. We also looked at the lifetime of these Feshbach molecules, so in-season Feshbach molecules. And one thing we find when we measure the lifetime of our molecular cloud, we see the decay is not described by one-body decay, but it's basically entirely described by two-body decay. So basically what's happening is two Feshbach molecules collide and then vibrationally relax. So basically, since in the Feshbach state, you're in the highest vibrational state, in a collision, they can actually relax to lower states. And that is the dominant process. And it turns out it seems to us that it's almost a unitary, unitary decay. Almost every collision leads to a relaxation event. But it doesn't really matter so much to us because the lifetime at these densities that we have is still 5 milliseconds, and that's long enough to do steer up into the ground state, which is what we care most about. But there might be actually interesting physics with condensed or degenerate Feshbach molecules. Again, that's a question. There has been some theory work on that, and any input and suggestions of what one could look at here would be quite exciting for me. Okay, towards the NaCs ground state molecules. So now we are here at our third step, and what I'm going to tell you now about is all preliminary. I never spoke about it before, and it's very, very new data. So we want to go from the Feshbach state to the ground state. So here you see the relevant Born-Oppenheimer potentials, also some work from Mott from a few years ago. And we believe by using two lasers that are targeting a state in the C triplet sigma / B singlet pi potential, we should be able to get a bridge to the absolute ground state. So the task is that from Feshbach molecules that are dominantly triplet in spin character, you need to find a bridge to go into the singlet ground state. So you need an excited state with singlet triplet mixing. And we believe it's somewhere in that range. So to actually find a state, we did extensive single photon spectroscopy of electronically excited states. So these are 4,000 data points taken on several days. And I'm a little bit proud of that data because it kind of shows how stable the baseline of our molecule number is over many days. So basically you switch on the machine and we have almost reproducible atom numbers, and with that also molecule numbers. So we did similar work like that with NAK at MIT like a few years ago. It took us months. Basically this data we took in a week or less. So this was quite effective. So this scans over like, I don't know, maybe 8 or 10 vibrational states. And then we pick like one of them and zoom into it and try to understand the rotational features of this state, and try to assign quantum numbers and try to figure out a state that can go coupled to the ground state. And actually it turns out basically concurrently, just a few months before us, Kang-Kuen Ni, who works on single sodium cesium molecules, has actually also located this excited state and figured out this feature as a potential one to go to the ground state. So with this feature located, we need now our steer-up laser system. Steer-up lasers need to be phase coherent. So you need to have two lasers that are phase coherent, but the color is completely different. So your only chance is to basically stabilize the absolute frequencies of the lasers extremely well. We anticipate that we need, oh God, what's going on? We anticipate that we need kilohertz line widths. And so we built a home-built diode laser and use a commercial tie stuff laser and lock them to high finesse, ultra low expansion glass cavity in a vacuum chamber. So basically, the setup is largely home built. And with that, we try to locate the ground state in 2-photon spectroscopy. So we want to do outlet hounds and EIT spectroscopy to locate the ground state. Basically, shine in the laser here on the down leg and see the state splitting in the excited state while probing it with the up leg laser. And here we see it. So at some point, we located the ground state. So that's maybe 2 months ago. This is outlet hound splitting. So that serves also as a measure of the Rabi frequency of the down leg laser, which thankfully is quite high because we use a kind of low power diode laser. Having 45 megahertz there is very nice. And it allowed us to measure the binding energy precisely also of this molecule. So that's great. So it's very close to getting to the ground state. And actually, it turns out just a few weeks ago, we managed to go to the ground state of sodium cesium. So we are very excited about that. So this is the stir-up sequence where you are actually ramping the intensity of the up leg and the down leg laser in this sort of counterintuitive way, and adiabatically transform the Feshbach molecular state into the tightly bound molecular ground state. And our efficiency is not groundbreaking yet. It's 40% of a single trip of stir-up. But still, we create about 6,000 sodium cesium ground state molecules at a reasonable density of 2 × 10⁻12 per cubic centimeter. Technical improvements are underway to actually boost the stir-up efficiency. So we have improved the line width of the lasers, and it's now actually, as we speak, they are trying to do another stir-up run. Besides going to the ground state, well, we can also start to see what happens when we apply electric fields to our molecules. So what happens when we apply electric fields to the molecules? Well, I mentioned already before, basically what you do is you line the dipole moment in the lab frame. But on the physics side, what happens is that with the electric field, with the Stark term here in this Hamiltonian, you couple opposite parity rotational states. And that effectively leads to alignment of the dipole in the lab frame. And here you see, again, this plot that I think I showed before, induced dipole moment versus electric field. And for sodium cesium, we should see 2.5 dBi of induced dipole moment at 2 kilovolts per centimeter. So it's fairly moderate electric field. So, well, we went ahead and put electrodes around our vacuum chamber, ITO-coated glass plates outside of the vacuum chamber that can actually take electric fields up to ± 8 kilovolts. And with that, we did Stark spectroscopy and go all the way to fields that corresponds to a dipole moment of 2.6 dBi. That is the largest dipole moment induced in ultracold dipolar molecules so far. So we can go back with that number to our phase diagram and try to figure out where we are in this phase diagram. So we have 2.6 dBi, which translates to a dipolar length of 8 micrometer effective range. The interparticle spacing is around 630 nanometers. That gets us to an RD of 13 right now. So we are right now there. So still in the superfluid regime. But actually, we just figured out a way last week to boost the electric fields from 8 kilovolt to 12 kilovolt. And that change will give us RD22. So with conditions that are within reach, we are somewhere just above the crystalline phase transition once we put our system into D. So that's a very exciting place to be. And we are currently setting up. Actually, we have our molecules already prepared in what is called the accordion lattice. So it's 2 interfering laser beams that can be tuned in angle. So you can actually compress your trap from a 3D trap to a 2D plane. And we will push this and see where we end up with in terms of phases. Okay, so I think time is advanced quite a bit. So I just want to flash very briefly our second experiment in the group. It's non-related to molecules, but it is related to long-range interactions. And it is related to the emission properties of atoms. When you have an atom or a quantum system just sitting by itself, it decays. Exponential with the exponential population decay, and that is basically this spontaneous decay is limiting your coherence. It's relevant in many quantum systems, and it would be great to actually find ways how to improve this exponential decay. We try to look at it with neutral atoms, and basically the idea is to have many atoms next to each other. Let them interact radiatively like antennas in a way that spontaneous emission is suppressed. And this suppression of emission, if done correctly in an ordered array, is called subradiance. However, achieving subradiance in ordered arrays is not completely trivial because the distance between the atoms must be larger than the wavelengths of the emission or half the wavelengths of the emission. So achieving that is an experimental challenge that we try to tackle. One amazing thing, though, is that subradiance is one of the few effects that actually become better when the system is bigger. So the more atoms you place next to each other, the stronger the suppression is. It actually turns out that the suppression goes as 1/n³. So that's a very interesting effect that's kind of different from most other things in quantum systems, where if you add more, it gets worse. So the name of the game is minimize the distance between atoms and maximize the wavelengths of the transition to actually observe this. So can we do this in the lab? Well, we have put together a collaboration of Ana Arsenio Garcia on the theory side, who has worked a lot on subradiance, quantum photonics group or nanophotonics group at Columbia, working on optical metasurfaces that may allow us to actually create traps that are very close to each other. And we are building the atomic system based on strontium to make this happen. And in strontium, there are many nice lines. I don't have the time to go through all the details, but basically, turns out that strontium offers conditions that allow realistically to observe subradiance, and we built the setup, started last fall, and work on arrays to actually trap individual atoms. So there are no atoms in here yet. That's just a magic wavelengths array for strontium with 900 traps. We have also created traps using holographic metasurfaces, where we are now working on pushing the distance between them to much closer. Just as a very recent results, we have built a new source also for strontium. We don't use a Zeeman's law, but a homemade 2D Mott system based on dispensers. And just last Friday, we got the 3D Mott of strontium using our homemade source. So with this collaboration, we are kind of pulling it all together, and hopefully we can see subradiance at some point, not in the not too far future. So with that, we actually managed to go through everything. And I just want to summarize. We created dual condensates of sodium and cesium. We created Feshbach molecules of sodium and cesium at ultra-cold temperatures. And actually, we managed to go to the ground state of sodium cesium, having a new dipolar system at our hands, which should allow us to really study exciting new physics, especially on the quantum simulation or new quantum phases side of things. But it's of course also a good system for studying quantum magnetism or for studying quantum chemistry of these molecules. And in the very end, I just told you briefly about the subradiance work. So with this, I want to give credit to my group on the sodium cesium and the postdoc Ian Stevenson, who is an absolutely phenomenal driver of this experiment. Grad students Aidan Lamb, Claire Warner, Nicola Bigali, have been each in charge of the pieces of the work that I presented. New grad students on the experiment are Silwei Chang and also Wei-Jin Yuan, just started the last year. And Emily Bellingham is an undergraduate on this experiment. And then on the tweezer experiment that I just showed in the very end, we have postdoc Minho Kwon. Wei-Jin Yuan is kind of doing double duty on both experiments, and we have master student Max Alto and undergrad Chuan Gan, and all of them just did amazing work in the last year. And I just want to take the opportunity of my first talk to thank all of them for making this this tour de force possible. And I also want to advertise at the very last thing that there are postdoc opportunities, and particular there are fellowships available in the New York area. So there is a New York Max Planck Center, and there's a new postdoc fellowship with the application deadline of October 15th. So if that's something you're interested in, please talk to me. And with a very ambitious deadline of 2 days from now, you can also talk to me and apply to the Simon Society of Fellows. That's a wonderful postdoc fellowship, maybe one of the most attractive ones that are out there from Jim Simons' foundation. Yeah, if you're interested in that, talk to me quickly. So thanks so much. And well, I'm happy to take questions.
Thank you, Sebastian. Let's start.
So with the dipolar molecules, how are you going to know if you made a crystal? So what signatures are you?
Yeah, no, this is a very good question. So the question is, yeah, I repeat the question. The question is how, if we create a dipolar crystal, how can we actually detect it? So this is actually a question that we are still thinking about. One possibility is actually trying to image it directly. So with sodium cesium, the dipolar lengths can be more than 10 micrometer, which means the interparticle spacing can be also several micrometers in the crystal. And it should be possible to image it with high resolution imaging. There is a problem. I mean, there is a challenge though, because in the traditional ways of how to image ultra-cold atoms with single site resolution is you have a pinning lattice and you cycle a lot of photons. So that will be tricky to combine with a crystal. Once you switch on the pinning lattice, you will destroy the order to some degree. But perhaps there's a way how to get around that. There might be even the possibility in 2D to image without the pinning lattice and not have too much momentum diffusion. We are thinking about that. Other possibilities to actually do a time of flight experiment. You should see it in the momentum distribution. And you can also see it as as modes of the many-body system, excitation modes of the many-body system. You can start shaking the crystal and see the spectral response. But of course, I think you may want to have seen it before you study spectral response. So these are our ideas about that. But other ideas are welcome, that's for sure.
Next,
Could you go over your experimental apparatus again? You prepare the two VECs in separate chambers and then transport them to overlap, or?
Yeah, so the question is about the production sequence of these dual condensates. So sorry for going a bit quick there. So we really make them all together. They are all, the sodium and cesium are together in the magnetic trap, and cesium is sympathetically cooled with sodium. So together all the time. And it works because we can tune to get the cesium scattering lengths under control. We can go to almost 900 Gauss, where cesium scattering length is about 300 Bohr radii, which is kind of uncritical. And luckily at that same place, the interspecies scattering length is like 30 Bohr radii. So it's fully miscible, and the mixtures thermalize with some time delay because the scattering length is so small, but they are always together. So that's why it's, works quite straightforwardly. Yeah, starting from the Mott, exactly. Yeah, the Mott is, completely, almost overlap, not completely overlap. Turns out it's a little bit better if you push them slightly back.
So I have a question about subradiance. Can you give some intuition on how it works and what role do interactions play?
Mm-hmm. So the question is about intuition about how subradiance works. Well, let me just say the following. By placing atoms around one atom, you modify the vacuum. You can, the more common way of doing it, you put a cavity around the atom, and then you modify the vacuum. That works completely, but this kind of may not be compatible with your experimental setup or may not be scalable. You kind of need one atom in one cavity. But here, basically, you use the atoms itself as emitters that modify the vacuum. And if you do it in the right way, you get a suppression of the emission of a photon excitation in the array. That's the quick answer.
So your slide said that your separation is less than the wavelength.
Yes. So it turns out in strontium, so there's two elements to that. Strontium has, for the intercombination line, which is 689 nanometers, you have a magic wavelength of 520 nanometers. So you can make very small structures out of light at 520 nanometers. So we hope that with the use of photonic meta surfaces, we can actually get trap spacings that are very, very small, getting a very high effective in A, and then get very small trap structures. The other possibility with strontium, which is probably the more canonical or in the more likely way of how to observe it, is there is a P to D transition at 2.6 micrometers, and using that, it should be possible. Strontium is also nice. I glanced over it. Strontium 88 is nice because it doesn't have a hyperfine structure. So all the physics of subradiance gets much more complex if you have substructure in the atom. So we try to be as clean as possible.
Anything else? Is anyone monitoring the chat on YouTube?
I don't think so. But Zoom people should feel free to ask questions. Where's Bill?
Sebastian, this is Paul Julian on Zoom. Can you hear me?
Yes, I can hear you, Paul.
Oh, very good. Yes. Well, I listened. This is beautiful, spectacular results you're getting. So that's good. I'm really glad to see that. I'm curious, though, on you mentioned evaporative cooling possibility for the molecules, but you're currently doing the cooling in the atoms rather than in the molecules. So given the fact that you can line up the molecules and get really fast elastic collisions, if you line them with an electric field, you might be able to evaporate very quickly. Have you thought about the prospects of doing cooling in quasi 2D with your molecules?
Yeah, I've thought about that, and that is there's basically two ways that I'm thinking of. One is basically just as you described, you do repulsive side-by-side interactions, and then you try to evaporate. A practical challenge is that you need to have a trap that basically allows the molecules to escape there. But it should be possible. Another possibility to actually induce repulsive interactions. So in a 2D trap, basically, you can only evaporate on the edge of the 2D system, which hopefully works well enough, but we don't know. Another possibility is this nice idea to go into the first rotationally excited state and use this first type resonance to do actually repulsive shielding of the molecules. And then you could actually think about evaporating in a 3D trap, and that might be even better. These are the two ideas.
Okay, no, that would be nice if you could do that. You didn't mention lattices with respect to the molecules. Do you have any plans at all ultimately to think about molecules and lattices, or are you going to be working with gases only for the foreseeable future? Yeah,
so lattices is actually another possibility. We basically have no proposal written about that yet, so maybe I should. But basically, starting with two BECs, it should be with overlapping BECs that are still sort of weakly interacting only with 30 A naught interspecies scattering lengths. It might be actually possible to really do quite nicely this old idea of making dual Mott insulators with a filling of one and then associate in the lattice. I think in sodium cesium that might be easier than in many of the other species. So it's something that is in the back of my mind, but we kind of right now we are pushing in the bulk and in the accordion lattice.
Great, thanks.